But I was just saying that here we have a quick agenda of the topics that we'll see on this presentation. So I will start introducing the institute where this project took place. Then we will talk about the problems that motivate the solutions that we created, how we developed these solutions, how we tested the solutions on a motivational use case, the results that we achieved with this validation, and of course, we proceed to the conclusion of the project. So, as I mentioned, this project was developed in a partnership with the Fraunhofer Institute for Production Technology, IPT. IPT is located in Nahen in Germany, and it is one of the institutes that compounds the Fraunhofer Group for Production of the Fraunhofer Gesellschaft, which is the world's leading applied research organization. And among their activities, IPT carries some projects with partner companies, with client companies, where they seek to bring innovative solutions for their manufacturing lines. And in this process, they analyze the research and development stages to the production process itself. So specifically, this final project work was developed in the production quality department of IPT. And in this department, in some projects with these client companies, the client company has a problem or an undesired behavior that happens on their manufacturing line. And they want to be able to predict these undesired behaviors before they happen so they can prevent it. So what they do is that they gather some data sets from their production line based on their measurements. They provide these measurements, they provide these data sets to the institute. They explain the problem, of course. And then from this point onwards, the institute starts a data science project following the CRISP-DM stage, which is a methodology for data mining, and that we can see the steps here in the image. And this is a really research-centric process. And on this data science project, the institute seeks to find mainly two outputs. So the first output would be the set of machine learning models that can make these predictions. And the other output would be the data transformations that we need to perform on the raw data in order to be able to fit these machine learning models in the best way. So these two outputs, they come from the evaluation stage of CRISP-DM. And at many times, these outputs are enough for the client company. So the company acquires this know-how, they acquire these machine learning models that were built based on the broad knowledge that the Institute already has about trailblazer machine learning solutions directed to production quality. So this just justifies why they seek the Institute to make this partnership. And then they can decide how to implement it. But the Institute realized in recent projects that sometimes it is also valuable for the client company to perform the deployment stage together with the Institute. So on that case, the client does not want only the machine learning models, but they want it already integrated with their production, being capable of performing these predictions in real time. So in specifically one precedent project, the Institute developed 4 machine learning models that were having satisfactory metrics and that were using advanced machine learning techniques. But when they proceed to the deployment stage, they found many operational problems, and this therefore made them to spend a huge amount of time on this deployment process that wasn't on the project schedule. So of course, the project suffered some delays, partially due to the fact that this guideline was something that changed while the process had already started, but also partially due to the lack of standards on how to develop the production application. So this is the problem that is the background of this final project work. And now maybe it's easier to understand the title of the project. So what we want to do, our goal is to come up with tools and other mechanisms that can integrate better the development and the operational stages, so we can enhance the path of these machine learning solutions to their deployment on manufacturing. So we want to speed up this productionizing process of the research application, but how can we do that? So in the beginning of the project, we mapped mainly 2 solutions. The first solution is to build a continuous integration pipeline, which will be automatically executing a series of integration actions while we are developing our production application. And the other solution will be to develop a series of software modeling diagrams that will tell the development team how to arrange the components and how to build faster this production application for this kind of projects. So these two solutions, they should stand as general solutions that can be used by the Institute in any future project of this type. So it was also on the goal of the thesis to validate these solutions, converting a data science project into a production application using the two solutions that I mentioned. So moving forward for the solutions, the CI pipeline, it's the solution that seeks to bring some automation to the process. So the idea of the CI pipeline is that we will have a Git repository, and whenever the development teams makes a new feature, whenever they make a merge request, so whenever we have a new instance of code on our Git repository, the platform should automatically trigger this series of integration actions. And specifically for our case, the final goal, what we want to achieve with these integration actions, is to have an isolated environment containing our application and containing all the dependencies that are necessary to run this application, so we can overcome the integration problems when deploying it. And this can be then easily deployed in production, just importing this environment created. So in order to do that and to build the CI pipeline, we need to configure two things for the GitLab platform. The first one is the GitLab Runner, which is the application that it is capable of running, of executing these integration actions. And the other thing we need to develop is a standard YAML file that the GitLab platform already understands as the file that it has to look in order to know which stages and which comments we want to execute in each CI pipeline trigger. So we developed 3 stages for the general CI pipeline. The first stage is the build stage, and this stage has only one job, which is called build Docker. And this job will be the one that will construct this isolated environment with all the dependencies that I mentioned. And this environment will, in practice, it will be a Docker image. So what this job will do is that it will gather all the programming files that were developed by the development teams. We'll arrange this inside the isolated environment. We will also have a requirements text file as an input that will describe which dependencies the build Docker job needs to install on this Docker image. And then, of course, you will also consult a Docker file that will properly instruct the job how to make this Docker image and which commands we want to be able to execute inside this Docker image when deploying this to production. So after building this Docker image, it will publish the image on the container registry of the GitLab platform. So it can be available to be used by other stages of our CI pipeline. And this is exactly what the test stage will do. So this stage has 3 jobs. 2 of these jobs are directed to perform software tests, which is the integration test job and the unit test job. So these jobs will verify, will validate if all the new features that were developed for the production application, if they are working as they were planned to work, and also if all the components of our software are well integrated. And they will publish the results of this tests, automatically on the GitLab platform, so the development team can look for those metrics in the future. And if any tests fail, then one of these jobs will fail. And if any job fails in the CI pipeline breaks. So then if this happens, we will not proceed to the release stage, and we will be avoiding to deploy an instance of our production application that has a bug, has an error, because deploying this can be harmful to the manufacturing. And as I mentioned, the goal of the CI pipeline is to enhance this path to deployment. So this is already one way to do that. The test stage has also another job, which is the linked job. And this is the only job in the whole CI pipeline that it is allowed to fail, because The lint job will only check for the coding styles that we are using if we are following the best practice established by the language. This is not something mandatory to follow, but it is nice to have a job that makes this verification and will throw a warning to the development team if anything is not following the best practice, but will not break the CI pipeline. So if we have the instance of our application already isolated and in one Docker image with all the dependencies tested, then the CI pipeline will proceed to the release stage. And on that stage, we want to take this instance of our application, make it available following a standard pattern. So the operational team, when making the deployment, they can know exactly which version of our application they want to deploy. So one way to do that is by establishing a tag to the release. And in our case, the tag has 3 numbers, one to indicate major changes, minor changes, and revisions. But we do not want to add the necessity for the development team to have to tell the CI pipeline which tag needs to be used in every release. They can do that manually, for example, when we have a major change, but they do not need to do that all the time because this would take out a little bit of the automation of the CI pipeline. So we have the validate tag job. This job will call a bash script that was developed, and this bash script makes some requests to the Git repository, verifies the tags that already exist in the Git repository, and then based on that, it will generate the next tag to be used. That will be the inputs of the release job. And of course, this job will properly make the requests to the release API, which will then make our application available. So this is the resulting workflow of the general CI pipeline, and we can briefly resume it as a series of integration actions that will mainly build our application, put all the dependencies together, and have an environment that can be easily deployed. We'll test this environment to make sure that everything is happening as expected, and then we'll make it available following a standard pattern to make the deployment even easier. So the CI pipeline will be the solution to overcome the integration problems, but it does not tell the development team how to properly make the production application. So it does not tell how the development team should arrange the software components of this application. And that is why the other solution was a series of UML diagrams that we created. And these UML diagrams will tell the development team what is a good way to architecture these types of applications. So for these UML diagrams, we were always following the solid principles while developing them, which is a series of design patterns that are used in order to achieve maintainable and reliable software architecture. And we also built these UML diagrams for 2 architectures, 2 deployment architectures where it's common to deploy machine learning solutions, which are the shared database architecture and the streaming architecture. But unfortunately, these UML diagrams, they are not very user-friendly to be presented in a PowerPoint presentation and explained it here. So one of the UML diagrams that we can show here and maybe use as an example of what the UML diagrams do is the sequence diagram. So the sequence diagram will tell the development team how to call the methods and how to make the interactions between the classes and packages that were listed and designed in the classes diagram. So here we have the sequence diagram for the shared database architecture, and we can see that we'll usually start these executions with an optional step where the main class has to interact with the configuration package to import some configurations. Then the main loop needs to get data from the database, so it will have to interact with the database package and the database instance. Then we need to transform this data and properly make the predictions. So we will have the main class interacting with the database package, with the models package, and also with the models package in turn will interact with the serialized files that contains our machine learning models. And in the end, we want to write these predictions back. So we need to, again, interact with the database package and the database instance. So, okay, we had these two general solutions, the CI pipeline and the software modeling. Then we, as I mentioned, we wanted to validate, then converting a data science project into a production application. And we did that using a data science project that was developed by IPT to be exhibited in some fairs and other exhibitions to show the activities of the production quality department. We took this data science project and we converted it into a production application, but since it was a motivational project, we also had to simulate the environments. We needed to simulate the environments to properly deploy the solutions there and test the solution that we created. So we created the simulation of both environments, the shared database and the streaming, so we could validate all the software modeling. Here in the image, we can see a diagram of the shared database environment, and we can see that it is really simple. It only has an instance of a relational database. It has a script that simulates the manufacturing publishing new data on this database. And whenever we want to do the predictions, we just need to run the container with the image of the production application we created. So it will read from the database, and then it will write the predictions back. But as I mentioned, we also simulated the streaming environment, and here we have some more complex components. So as you can see, we have also a Kafka Connect instance, which will automatically identify when a new data is arriving on the database. It will convert this data into event streams message, and will publish this message on Apache Kafka topics. And from this Apache Kafka topics, the streams that we developed and we want to deploy will read the information. Each stream will make the action that it is supposed to do. We'll write it back on the other Kafka topics, which will feed other streams. And at the end, the streams will publish the prediction back on the database also. So with these solutions, with the production applications that we built for both environments, we can talk about the results that we achieved, and we were able to correctly deploy and easily deploy the solutions, which already validates the software modeling that we did, since they were able to interact fine with the other components of the environment. And this is one of the major operational problems we usually have. So we tested both applications for different scenarios, and we wanted to validate against the worst case scenario. So for the deploy for the shared database application, what we did is that we got all the data that we had for this motivational use case. We put all the data on the database, and on a single execution of our application, we created all the predictions, and the application was able to handle all this data and write the predictions correctly back. And of course, for the streaming environment, it is a little bit different, because the streams were always alive and we're making the predictions in real time, since this is a requirement of the environment. So what we did to simulate the worst case scenario is that we simply published all the data at the same time. So the Kafka Connect generated the biggest possible amount of event streams messages, and all those messages were handled by the streams that we created, and we could see that using the Kafka control panel, we saw that no message was left behind. So again, this validates the software modeling that we did. And another interesting result that we got is that our CI pipeline proved to be really adaptable. Here in the image, we can see the results in CI pipeline of the streaming application. And as we can see, we had to scale it. We had to create other jobs to generate other images, but it was easy to do that because all the dependencies were already on the YAML file, on the GitLab runner. So everything was already there, and we could scale the pipeline, which was one of the goals of the thesis. And in conclusion, I believe that the solution that we created has a great potential to be expanded in future projects by the Institute, maybe creating other CI stays in the CI pipeline that can be more useful to a specific role of projects. And other colleagues of IPT already showed the interest in using this solution on manufacturing projects that will proceed now to the deployment stage, which makes me very glad and validates how the solution can be useful for the Institute. And of course, it had a huge impact on my formation, especially regarding how we can handle these challenging situations that it is to deploy these machine learning solutions on manufacturing. So that was everything that I had to share with you. I hope I was clear in my explanations, and now I would be glad in answering your questions.